In this video, we will talk about gravitational potential energy. In particular, we will define the gravitational potential energy of a system of particles. We will show how to calculate this gravitational potential energy for such a system of particles, and we will associate the law of conservation of energy with gravitational potential energy. Finally, we will solve a few problems based on these concepts. You may recall that in our previous videos, we have already talked about gravitational potential energy for a system such as this one, a mass above the surface of the Earth, and the distance from the surface of the Earth is h. Then we defined the gravitational potential energy U for such a mass m as follows. U equals the mass times the gravitational acceleration times the distance from the surface of the Earth, where we have taken the value of g to be 9.81 meter per second squared. However, this equation is only correct if the gravitational force, and therefore the gravitational acceleration, is constant over this height, or even if there is a variation in the value of g, it may be regarded to be so small that we can ignore it. In our present discussion, the mass m can be situated or located at any distance from the center of the Earth, so r has no restrictions imposed on it. It can be large, can be small, it does not matter. So the gravitational acceleration now will be a function of r, the distance from the center of Earth. We know that because the gravitational force F from the Earth on this mass m that pulls this mass towards the center of the Earth is also a function of r, and we have seen that the magnitude of that force is given by gravitational constant times the product of the two masses over the distance between them squared. Thus, the gravitational potential energy of such a system is a function of r as well, and it's given by the following equation: minus gravitational constant times the product of the two masses over the distance between them. Note, the denominator here is not r squared, but simply r. To understand the result for the gravitational potential energy that we have just written, let's look at the following system. Let's say you have a point mass m initially at a distance r2 from the center of, let's say, Earth, and under the influence of that attractive gravitational force F due to Earth, the point mass moves to a new position here, which is located at a distance r1 from the center of the Earth. So let's calculate the work done by this force F on this mass m as it moves from this point to that point. That expression for work is the integral of that force involved, which is a function of r, dotted into this displacement. Since the direction of the force is going in an opposite direction to that of that radial direction, let's call it r hat. R hat is the unit vector along the radial direction. Then we can write the expression for that attractive gravitational force in a following manner: minus gravitational constant, the product of the two masses, over the separation squared, r hat. This minus sign indicates that the direction of this gravitational force and the direction of this unit vector is opposite to each other. Substituting this force inside this integral and substituting the initial limit and the final limit, we get the following, which can then be integrated to give the following result: minus g little m capital M times minus 1 over r with the limits r1 and r2, which will simply be g m capital M 1 over R1 minus 1 over R2. But from our previous video, we know since gravitational force is a conservative force, the work done is related to minus the change in the potential energy. Minus the change in the potential energy is the potential energy at the initial point, namely that point, minus the potential energy at the final point, which is that point. By comparing these two sides of the equation, we conclude that the gravitational potential energy at some arbitrary distance is indeed given by the following result: minus g, the product of the two masses, over the distance between them. Let's look at the following three mass system. So you have 3 kg, 2 kg, and 1 kg masses, and they form the vertex of a triangle. The distance between them are specified, and we are interested in calculating the gravitational potential energy of this three mass system. The way we proceed is by considering two masses at a time. So let's first look at 3 kg and 2 kg mass. So that contribution will give you minus g. The product of the two masses is 3 times 2. The separation between them is 2 meters. The next pair is the 2 kg and 1 kg mass, and that's going to be minus g. The product of the two masses is 2 and 1. The separation between them is now 3 meters, so divide by 3. And the final pair is that 1 kg and 3 kg mass separated by a distance of 3 meters. And that's going to be minus g, the product of the two masses, 3 and 1, divide by the distance is 3 meters, which will give you a value of minus 3.11 times 10 to the power minus 10 joules. Now you see that this is a straightforward calculation without any reference to any angles, because potential energy is a scalar, so you do not need to consider any components. Let's see how we can associate the gravitational potential energy to the law of conservation of energy. So let's say you have a system, you have a sun, and you have a planet that's moving around it. At point number 1, the velocity of this planet is v1, and at point 1 it is situated at a distance r1 from the center of the sun. It moves all the way to point 2, where its velocity now is v2, and its location or distance from the center of the sun is r2. Since energy is conserved, the energy of the system when the planet is at point 1, E1, is the same as the energy of the system when the planet is at point 2. Let's calculate E1. E1 is a sum of two forms of energy. One is kinetic energy and potential energy. The kinetic energy is half times the mass of the planet. Let's call the mass of the planet little m. And the speed there is v1, so v1 squared. The gravitational potential energy of the planet at that location is minus g, the product of the mass of the planet and the mass of the sun, capital M, over r1. And that must be the same as the energy at point 2. At point 2, the planet is moving with a speed of v2, so its kinetic energy is half m v2 squared, and its gravitational potential energy is minus gravitational constant, the product of the two masses, over the new distance, r2. So in this equation, you have mainly 4 variables, v1, r1, v2, and r2. If you are given 3 of them, you can determine the 4th one. To give you an idea of how this calculation goes, let's look at problem 1. A comet travels around the sun. If the comet has a speed of 2 times 10 to the power 4 meter per second at that distance from the center of the sun, calculate its speed when the distance from the sun is 4 times 10 to the power 10 meters. Assume the mass of the Sun is 2 times 10 to the power 30 kg. So the comet was initially at a point where its speed is 2 times 10 to the power 4 meter per second. So its kinetic energy is half times the mass of the comet times 2 times 10 to the power 4 squared. So that's the kinetic energy of the comet at point 1, or the initial point. The gravitational potential energy is given by minus gravitational constant times the product of the two masses, mass of the comet times the mass of the Sun, 2 times 10 to the power 30, that is, divide by the separation distance from the comet to the Sun, and that's given by that, 3 times 10 to the power 11. And at the final point, its kinetic energy is half times mass, the new speed we don't know, that's what we want to determine. Its gravitational potential energy is minus g, mass of the comet, the mass of the Sun, which is 2 times 10 to the power 30, divided by the separation, which is 4 times 10 to the power 10. By conservation of energy, these two numbers must match. They are the same. Energy is conserved. And we can solve for the only unknown, which is v. Now you notice that the mass of the comet cancels out, so we don't need to know what the mass of the comet is. So when you solve for v, we obtain the following. 7.9 times 10 to the power 4 meter per second. And that solves the problem. Problem 2. Calculate the escape speed, or escape velocity, on a spherical planet whose radius is 450 kilometers and whose gravitational acceleration at the surface is 4 meters per second. So let's define what an escape speed is. An escape speed is a minimum initial speed of a particle that causes the particle to break free from the gravitational pull of a planet and move forever all the way up to infinity, where theoretically it comes to rest. So the initial point is the launching point, and the final point is indeed infinity. So let's apply the conservation of energy to this problem. So at the initial point, the kinetic energy is half times the mass times the escape velocity that we are interested in calculating. The gravitational potential energy is, as before, minus gravitational constant, the product of the masses, over the radius of the planet. At the final point, as we said, it will come to rest. So the kinetic energy is 0, and the potential energy is, of course, 0 as well, because now it is at an infinite distance from the center of the planet. Equating these two values, we get the following result. So the mass of the object cancels out, leaving us with this following result. However, we do not know the mass of the planet, but we do know that the gravitational acceleration at the surface of the planet is 4 meters per second squared. We also know that the gravitational acceleration at the surface of a planet is given in terms of the mass of the planet and the radius of the planet in the following way. G times the mass of the planet over the square of the radius of the planet. Now this is a result that we have seen in our previous video. So from this result, we find that little g times the radius is quite simply capital G, mass of the planet, over the radius of the planet, which is the term in here. So the right hand side of this equation is simply little g times the radius of the planet. And the escape velocity, or the escape speed, can be computed in the following manner. 2 times 4, which is this gravitational acceleration on the planet, times the radius, which is 450, converted into meters, square root, which will give you 1,897 meters per second. And that solves the problem. Thanks for watching.